Okay, so we're starting our trig unit. And in this unit, we're going to be studying the three basic trig functions, which you guys did learn last year. Does anybody remember what the three basic trig functions are? That's not the functions.
Cosine and tangent.
Sine, cosine,
These are going to be hard.
and tangent.
So are we working with like triangles?
Kind of. You used SOHCAHTOA to help you remember what sides of the triangle you used to figure out your sine, your cosine, and the tangent. But yes, you used your sine, cosine, and tangent. So these functions are based in geometry off of a circle and the rotations around its center. Sometimes the trig functions are also known as circular functions. So some people call them trig functions, some people call them circular functions because it creates a circle, and you'll see that as we go through some stuff there. So in this introductory lesson, we're going to introduce some basic terminology and concepts concerning angles. Some of the terminology is specified below. So we're going to go through some vocab words, and then we're going to go do some problems using those vocab words. So first thing I want to go over is our coordinate plane over here. So remember, this is your x, this is your y-axis. Where is our quadrant 1?
On the left, top right.
No.
That little bad boy right there.
Top right is quadrant 1. And then over here, top left is our quadrant 2. And then our quadrant 3 and our quadrant 4. So our first word is standard position. An angle is said to be drawn in standard position if its vertex is at the origin and its initial ray points along the positive x-axis. So what that means is you have a ray along that part of the x-axis going to the positive end of it. And then you have another part of it that is somewhere else, the vertex of it being at the origin. That is what we call our standard position. So generally we draw an angle showing that the angle opens up in a certain direction. This one opens up in the positive direction going that way. It is obtuse. And then this side over here is what we call the terminal ray, because that is where the angle ends. It terminates there. It stops opening up there. So that's why we call it the terminal ray. So we have two kinds of rotations. We have a positive rotation, and we have a negative rotation. So a rotation that goes counterclockwise, so it starts here and it goes counterclockwise in that direction, is what we call a positive rotation. You would have a positive number of degrees that you're trying to figure out for your angle, like 35 or 175. A negative rotation goes clockwise, so it would go down first and then around. Our next one is what we call coterminal angles. Coterminal angles. That involves your terminal ray side of your angle. So as I said, this side right here is my terminal ray. So we have one angle that goes this way. Your coterminal angle would come around that way, and they share that terminal side. So this one would be a positive, let's say for example, 120 degrees. Its coterminal would be a negative 240. It comes around the other way and meets and shares that terminal side. So if I would take the absolute value of my 240 and I added it to my 120, what do those two angles add up to? Yeah. So we're going to add to 360. There's always going to be 360 degrees in between the two of them. And then our last vocab word for right now is our reference angle. going to be doing a lot with our reference angle as the unit goes on, but for now we're just going to practice finding them. Your reference angle is an acute angle. So if it's acute, what is its degree measure? Less than 90. So it's between 0 and 90. So it's an acute angle that's formed by the terminal ray and the x-axis. So again, for the one we have drawn up here in the second quadrant, my reference angle would be this little acute angle here in purple that goes from the x-axis and then it would go up there. That's where your reference angle would be. And it's always between the x-axis and that terminal side. It's never dealing with the y-axis. Okay. Let's do some practice here. So example 1, for each of the following angles given by the Greek letter theta, draw a rotation diagram and identify the quadrant that the terminal ray falls in. So for a rotation diagram, we're going to need our quadrants here. Not really. So 145 degrees. That's going to start on the positive x-axis side there. They're all going to start at the positive x-axis side there. So if I go up here to my y-axis, how many degrees is that? And then over to here would be, and then 270, and then 360. So you got to remember, those go up by 90s there.
I knew the answer. I just wanted to hear it.
So 145, that's going to fall between the 90 and the 180. So you're going to draw your terminal ray over there. For the rotation diagram, you have to include your arrow showing which direction the angle is opening up in. Since it's a positive 145, we're going to go counterclockwise.
Oh.
And our terminal ray is in quadrant 2. And that was the other thing they want us to state, is what quadrant is the terminal ray in? Quadrant 2. Yes. So 320, again, I put my first part of my angle on the positive x-axis. It's always going to start there. 320, well, here's 90, 180, 270. So it's going to be down here. In which quadrant? Quadrant 4. And again, you've got to have that arrow going around showing it's 320 degrees, so it's almost making a complete full circle. Showing which direction it's going in. Okay, 72. What quadrant are we going to be in? Quadrant 1. Yes.
What is the reference angle of more than 90 in that?
In which one? No, the reference angle would be 72. In quadrant 1, the angle is its own reference angle. But we'll talk about that later. Right now, we're just practicing figuring out where the angles are. So one thing at a time. So for D, first negative angle, we have negative 210. So it works just like the other ones, except you're just going to go backwards. So this would go negative 90, negative 180, negative 270. So negative 210 would fall there in between the negative 180 and the negative 270. So just like we did, this time our little arrow is going to go down and around instead of up and over. And our terminal ray is in quadrant 2. My board froze.
No math.
That's level 40. Well, I get like brain farts after like working.
All right, 250. Which quadrant are we going to be in? Third one, so we're going to be down here. 250 is actually a little closer to 270, so you kind of want to put it a little closer to that 270. Okay? So we are down there in quadrant 3. All right, how about negative 310? Yes, that one's going to be up in quadrant 1, and since it's negative, it's going to go down and around. So now for 460, that one, it's going to go all the way around once, and that's going to be 360. And then how much more is it going to have to go? I drew that in the wrong spot. So it's going to go around, and then it's going to go 100 more, so that's going to be over in quadrant 2. So our terminal ray being quadrant 2. And you got that little spiral going around, showing that it's gone around one full time before it ends up there in quadrant 2. So then our negative 400 is going to do the same thing, only it's going to go the other way. So negative 400 is going to go down and around one full time. Quadrant 4, because that's negative 360, so we only have to go 40 more degrees. So we would end up in quadrant 4. So on the back page, example 2, in which quadrant would the terminal ray of an angle drawn in standard position fall if the angle measures 860 degrees? So we have two ways we could do this. You could sit here, draw your little rotation diagram like we were just doing and figure out how many times it's going to go around. Or you could just do some subtraction. 860 minus 360 would give us 500. That's still a little too big, so I'm going to subtract 360 again. And what do we get? 140. So what quadrant would 140 fall in?
3, 2.
2. So if you were to draw it, it would look like this. It would spiral around twice and then go into the second quadrant. Yep. All right, example 3, give a negative angle that is coterminal with each of the following positive angles, which they've used alpha now to represent the angle. So I'm going to draw a little picture here. They gave us 90 degrees. So here's my 90 degrees. So again, our coterminal angles mean it's an angle that goes in the other direction because they want the negative one specifically this time. It's not in a quadrant. It's what we call a quadrantal. It's one of the lines. So our coterminal side comes around and meets it. So what would this angle measure be? Negative 270. Because it goes around in the other direction. So your coterminal just basically kind of completes the circle for you. Yep, negative 270. So B, we've got a 330. That's down in quadrant 4. So I draw my 330 first. So then my coterminal is going to come down here, and it's got to finish off the circle. So my coterminal angle would be negative 30. All right. So for C, what quadrant is 120 in? Quadrant 2.
Wait, can't we just like subtract? So like 120, so like 360 minus 120 is 340.
But since I want the negative one, I would actually want to do 120 minus the 360. And it would be negative 240. But yes, that is another way we can do it. Subtract them. So then our 210 falls in which quadrant? quadrant 3. So what would be our negative coterminal angle? Negative 150. Again, if you can't figure it out in your head, 210 minus 360. There's our negative 150. You could have done that for the first two also. Now your coterminal angles don't have to be negative. You could have positive ones. So like for example, for this 90, I could have a coterminal angle that goes all the way around once and then comes up and meets the 90. So you could have 360 plus 90, 450 is another one. So you can just keep adding 360 to each angle, and that will give you another coterminal angle also. It's just this time we wanted specifically the negative ones. All right, example 4, coterminal angles drawn in standard position will always have measures that differ by an integer multiple of what? What do they always have? 360. They always have a difference of 360, which is what I was just saying. Keep adding 360, you get another coterminal angle. Add 360 again, you get another coterminal angle. Add 360 again. Or you could subtract it and get negative angles. All right. Beta is just another letter. These are all Greek letters. Theta, alpha, beta. So this time we're going to switch it up a little bit. We were doing our coterminal angles. They share that terminal ray. This time we're going to look for our reference angles. So 160 degrees would be an angle that is over here in quadrant 2. Here's my rotation diagram for my 160 degrees. As I was saying on the front, your reference angle is this angle that goes from the x-axis to your terminal ray. So this side of the x-axis is how many degrees? 180 degrees. So you're basically figuring out how many degrees between 160 and 180? 20. So our reference angle would be 20 degrees. So my next one is 300. So that's over there in quadrant 4. Yes, because it specifically said draw a rotation diagram. Okay. So again, our reference angle goes from the x-axis down to the terminal ray. So this one would be 60 degrees.
Are there ever negative?
Reference angles are never negative. So then C 210 is down here in quadrant 3. So our reference angle
Would it be
would be this little angle here.
30?
It is 30.
How do you decide between choosing either 180 or 270?
You never use 270 because that's the y-axis. Reference angles are always connected to the x-axis. So you're using basically 0, 180, or 360. Because reference angles are always less than 90. So for this next one, it's 78 degrees. So our reference angle is just 78 degrees because that's already an acute angle and it's already connected to the x-axis. That's your reference angle.
So if it's obtuse, it's not.
Okay. All right, let's try these 4 down here. Negative 110 degrees. That's over there in the 3rd quadrant. Our reference angle would come down from the x-axis to meet the terminal ray there in the 3rd quadrant. It wouldn't be negative, it would just be 70. So our reference angle would be 70. Reference angles are never negative. No.
Yes. Just like at practice, expect we're always going to run. Expect this always is going to get harder.
Negative 280 would be just barely into the first quadrant, because remember that one quadrantal up there is negative 270, so it's just a little bit past it. Our reference angle would come up from the x-axis, and it would be what? 80. For our 605, let's subtract 360 from it.
Is it in the second?
I don't know. 245. So you're both not right. It would be down here. But it goes around one full time, and then it comes and meets in the third quadrant. So even though it still wraps around once and then it comes in the third quadrant, that doesn't matter. Your reference angle is still this little acute angle going from the x-axis to where that terminal ray is. So you could do your 245 minus 180. So our reference angle is 65. So negative 410. It would wrap around one whole time. That's negative 360. So we need to go how many more degrees? 50 more. Which that would also happen to be your reference angle. 50 degrees. Radian angle measurement. All radians is, it's just another way of measuring your angles. We're very used to degrees. We use degrees very often. Radians, as I said, just another way. And radians just connects your angle to the arc that it cuts off, because it makes a little full circle. So just as distance can be measured in inches, feet, miles, centimeters, etc., rotations about a point can also be measured in different ways. Degrees and radians are the most common ones. So a common unit of measurement, radian. The radian angle, theta, created by a rotation about a point A using the radius passing through an intercepted arc, gives us this formula, S equals theta R, or theta equals S over R. Does that look familiar? You did a little bit with it last year. So let's see where this all comes about from. So consider a full rotation about any point in the counterclockwise direction. So here we have our axes. I'm starting in standard position. So then let's say my terminal ray is also here. So that means it went up and around, and it came back to the same position. So a full 360 degrees. It makes a circle. A little bit. So that's why we always say things are a circular function, because if you take it and you go all the way around that 360 degrees, it creates a circle. So that's why we're going to be using circles a lot for this. So they want to know, what is the arc length S in terms of the radius of the circle for a full rotation? So if I started here and I follow my line, what am I doing around the circle? I am, yes. What do we call it when I go all the way around a circle? Yes, circumference. So the arc, which we use letter S, for a full 360-degree rotation is the same as your circumference, which what is our circumference formula?
Wait. S equals
What is your circumference formula?
theta r.
No.
Radian squared.
2 pi times the radius?
2 pi r squared.
No.
Wait, what's 2 pi r squared?
An area of a circle multiplied times 2. All right, so as I was saying, one full rotation, the arc is what we refer to as 2 pi r. 2 times the radius times pi. Because it's like your circumference. The S is like your circumference formula because you go around the whole outer edge of a circle, which the formula is 2 pi r. So based on the definition above and on your answer to part A, how many radians are there in one full rotation? So our formula above is S equals theta r. We just figured out S for one full rotation is your circumference formula, 2 pi r. So that's going to equal theta r divided by r. So 2 pi equals theta. So it's 2 radians, 2 pi radians equals one full rotation. So radians essentially measure the total number of radii that have been transversed about the circumference of a circle in a given rotation. I know that doesn't make a lot of sense to people. All that's saying is radians measurement compares the radius to the circle. That's how we get the radian measure. So based on the circumference formula of a circle, there will always be 2 pi radians in one full rotation. So 360 degrees is always going to be 2 pi radians every single time. So use your formula above to answer the following situations. So sometimes what we have to do is we have to figure out what the arc, the radius, or the angle are. So determine the number of radians that the minute hand of a clock passes through if its length is 5 inches and its tip travels a total distance of 13 inches. So the 5 inches would be which letter of our formula? R. The length of the hand is 5. And then the very tip of that hand travels 13 inches. So what is that going to be? The S. So then we'll plug that into our formula. So 13 equals theta times 5 angle in radians. Let's go to the decimal. We'll go to the nearest tenth with our decimal. What do we get? 0.6. Good. So we'll plug this into our formula. And then all you got to do is a little multiply. 0.55 times 8. 4.4. So the arc that's cut off by that angle that's opened up would be 4.4.
What was 8.45?
4.4. All right, so radians are essential in the study of higher level mathematics and physics and are the angle measurement of choice when you get to calculus. So it is important to be able to convert between the angular system of degrees and radians. The next exercise, we're going to actually practice that. Now, I'm not going to lie, a lot of this stuff when they gave me radians, I generally convert it to degrees because that's still what I'm more comfortable with. So being able to convert back and forth is going to be extremely helpful for you guys.
There's a hair on your right arm.
Yeah, there usually is.
It's
So consider 1/2 of a full rotation. So a full rotation is how many degrees? 360. So half of a rotation would be 180 degrees. We said a full rotation was 2 pi. So half of a rotation would be what? 1 pi. So this is why we generally say 180 equals pi. And that's where that comes from. In radians form, yes. What? 360 was 2 pi radians. Since I have half a rotation, 180 is 1 pi radians. So using the two equivalent angles of rotation in A, that 180 degrees is the same as 1 pi radians. Convert a 30-degree angle into the equivalent angle in radians form. So what we do is you take your 30 degrees and you multiply it times pi over 180. Close. You're just missing a very important part.
1/6 pi.
You would end up getting 1/6 pi.
Oh.
Because when I multiply, 30 is the same as 30 over 1, because now I have two fractions I'm multiplying, makes our lives a little easier. 30 times pi is 30 pi. 1 times 180 is 180. Reduces to give you that. 1 pi over 6, or you could write pi over 6. It's the same thing. So 30 degrees is pi over 6 radians. So let's try this again. Let's keep practicing this. So 90 degrees, I want to turn this into radians. So I'm going to multiply it times pi over 180. Or simply pi over 2. You could put the 1 pi over 2, but generally you're going to see it as pi over 2. So for part B, it'd be 120 times pi over 180. Now some people aren't very good at being able to reduce this in their heads, and that's fine. So what you would want to do is you would multiply again. You put this over 1. 120 times pi is 120 pi. 1 times 1 gives us over 180. You can use your calculator to help you reduce. So I'd go to my calculator, and I would do 120 divided by 180. And then I push my math, enter, enter, and it would reduce it to 2/3. You just got to remember to put your pi with your numerator. So this would be 2 pi over 3 radians. So then for our letter C, again, you would do 225 times pi over 180. What would that give us?
I got 5 pi over 4.
This should be 5 pi over 4.
Oh, wait.
Math, enter, enter, 5 pi over 4. So for the next one, we're going to go the other way. We have radian measure. We want to make it degrees. As we said at the top of this page, 1 pi radians is how many degrees? No? 180. So if you have a pi there and you're told to convert to degrees, all you have to do is plug 180 in for your pi. No. So you do it for the next one. We're going from radians to degrees. I know 1 pi is 180 degrees, so I'm going to put 180 in there. What? Oh, I thought you just said 70. So it's 270 degrees. And then our last one here again. 180 goes in for pi.
Half the
135.
135 degrees.
Oh, God.
Yes.
Oh, God.
So sometimes radians is not always going to have a pi symbol with it. So you still have to be able to convert between your radians to your degrees. So if there is no pi symbol, you just multiply it times 180 over pi. So it's the opposite of what we were doing before to go from degrees to radians. You just flip it, and that takes you from radians to degrees. So when you type that in the calculator, you are actually going to use your pi button. So type in 5.8 times 180 over pi.
332.315.
So it's the nearest degree.
Oh, about that.
Yep, nearest degree.
Little carrot.
The one above the little exponent thing. So you had to hit second the exponent button. So do the same thing for B, multiply it times 180 over pi.
Instead of like a 0.5, you round up.
Yes.
No, you said it's,
So 4.2 radians would be what is degrees?
241 degrees.
241 degrees. And then for C, negative 2.5 radians. Negative what? 143 degrees.
So 1 radian is what?
1 radian, no, it's 1 radian ends up being in the first quadrant still.
What makes it go all the way around?
2 pi radians. Goes all the way around, makes a full circle. 2 radians, you got to multiply it times pi, 180 over pi to figure out what the degrees are. So like for this example here, we have an angle drawn in standard position whose radian measure is 2 radians, would terminate in which of the following quadrants? Again, I even struggle a little bit with being able to take my radians and tell which quadrant 2 radians is going to end up in. So you want to do like what we were just doing. Turn it into degrees. So do 2 times 180 over pi. $115. So what quadrant would 115 be in? Quadrant 2.